Welcome to the lecture first lecture for June 13th. We're going to talk today about carbohydrates. In particular, we're going to talk about monosaccharides. The next lecture, we'll talk about di and oligosaccharides, talk about the glycosidic bomb, but today we're going to talk about just sugars. We'll talk about sugar through the rest of the semester. I just want to introduce kind of a case study topic on diabetes, and I normally put in a little case study and a question at the beginning, but I'm going to dive right in right now. Diabetes is when your body is not producing or has lost sensitivity to insulin. When it's not producing, type 1, when it's lost sensitivity, type 2. Insulin is a hormone. We'll talk about it probably 6 more times in biochemistry. That's the hormone that's needed to convert sugar and starches and other food into energy. And insulin is produced in the pancreas. Again, two types of diabetes. Type 1, body does not produce any insulin. Type 2, usually that's onset youth ages, maybe preteen years or teen years. Type 2, body's not making enough insulin or is losing sensitivity to insulin being made. That's usually later in life as you get into adulthood. Unfortunately, diabetes is increasing in prevalence. At the current rate, 1 in 3 Americans will have diabetes by 2050, and 9.3% of Americans suffer from diabetes now. It's the 7th leading cause of death in the country, and in a couple of years it'll be a lot worse. This is because of our diet. I'm not going to sugarcoat this. This is a significant problem, and as pharmacists you will see this problem on a daily basis. So, in a cell, we have an insulin receptor. What happens is insulin comes in, binds glucose on the outside of the cell, goes to the inside of the cell through the glucose channels. We'll talk about this again later. That's just the general theory. So what happens is if we don't produce insulin, the glucose channel never opens and glucose doesn't go to the inside of the cell. Or if the insulin receptor is not as effective as it used to be, there's several mechanisms by which that can happen, then glucose doesn't enter the cell either. So one of the things, glucose is very toxic, and the reason that is because it's a very oxidizing molecule. It's highly oxidative, and that's important to know because if you have persistent glucose, not only you'll have a chronic condition of highly oxidative molecules running around, and it's a risk factor for infection. And this concept is also important because when we talk about glucose, that oxidative, because of the fact it's oxidative, it has it'll form massive structures, which we'll talk about in the next lecture. Risk factors for diabetes include weight, inactivity, family history, and race. Your age, if you have gestational diabetes occurs when you're pregnant, so that's a very unique subset. You can have polycystic ovary syndrome, high blood pressure, abnormal cholesterol and triglyceride levels. Now you know why I've worked so hard to get rid of my triglyceride levels being so high. So that's the discussion, and diabetes centers on carbohydrates. So let's talk about what this means. So carbohydrates have the formula CnH2ON. They're produced from carbon dioxide and water via photosynthesis in plants. They range from small glyceraldehyde, which is a 3-carbon, has a molecular weight of 90 grams per mole, to as large as amylopectin, which is absolutely enormous and is hundreds of thousands, if not millions, of glucose and other carbohydrate subunits put together as monomer subunits put together into big polymer chains. So when we talk about carbohydrates, there's 2 different kinds, aldoses and ketoses. Aldose contain an aldehyde group, and a ketose contains a ketone functional group. So we have glyceraldehyde, which is a 3-carbon carbohydrate, and you can have dihydroxyacetone, which is a ketotriose, which is a ketose. So yeah, both of those are very, very important, those concepts. So you'll want to know that an aldehyde has the aldehyde, or an aldose has an aldehyde functional group, and a ketone has or ketose has a ketone functional group, and you'll want to know the difference between the two. Some of the things that happen when we talk about sugars. First and foremost, we have enantiomers, and this is going to bring back bad memories from organic chemistry, but enantiomers are stereoisomers that are non-superimposable mirror images. In sugar, they can have many chiral centers. The only one that's important is the one that's distant from the carbonyl carbon, and it's designated, we're going to designate this either as D or L. So on the left you have D, on the right you have L. Hopefully I said that right. D on the right, L on the left. Sorry, hopefully I said that right. And you can see this is glyceraldehyde again, and you can see that they're mirror images of each other, and so this is the important, this is a very important, you will see this on your exams, enantiomers. So diastereomers are stereoisomers that are not mirror images. Diastereomers have different physical properties than their counterpart diastereomer. There's an example of these right here in aldoses, and you will see that D-erythrose and D-threose are diastereomers. They have very different properties. So the important part here is that you note that there are multiple chiral centers in these molecules. These are very common in nature, and you'll encounter these in later chapters. But note that even though they have the same functional formula, they are very different molecules. Again, diastereomers are stereoisomers that are not mirror images. The other concept, you may or may not see diastereomers on your exam, but you will see epimers on your exam. Epimers, this is an example of that. D-glucose and each of its epimers are in this example. So D-glucose is in the middle. It's two of the epimers on either side. We have D-mannose, it's an epimer at C2, and galactose is an epimer at C4. And what you see in an epimer are two sugars that differ only in the configuration around one carbon atom. So they can be a lot of different things besides just epimers, but epimers in particular are two sugars that differ only in configuration around one carbon atom. So these are all epimers of each other. Very, very important concept for your exam, and I would just know the concept and be able to look at it and see. So some structures you're going to want to know, just right off the bat and memorize, because you will see them all over the place. Ribose is a standard 5-carbon sugar. You're going to see that in DNA. We've already seen that one DNA. We'll probably see it again. Glucose is the standard 6-carbon sugar. Galactose is an epimer of glucose. Mannose is an epimer of glucose as well. Fructose is the ketose form of glucose. All those are important to know. I would just memorize them. There's not much else to say about it. Just memorize those because you will see them over and over and over again. Okay, so D-aldoses, we've already kind of shown this. The important part again is note that they're chiral centers. Here are the ones that are, these are just memorizable as well. You're going to want to memorize these. We'll see glyceraldehyde a few more times, as well as some of the other D-aldoses. Some larger chain D-aldoses, you got ribose, arabinose, xylose, lixose. Those are all larger aldoses, and the sugars in the box is the most common name in nature, and again you'll probably encounter most of these. You'll see xylose, you'll see the left three, ribose, arabinose, and xylose, very commonly in nature. These are the 5-carbon. 6-carbon aldoses, you'll see glucose, mannose, and galactose. This chart is mainly for your reference. These are the 6-carbon aldose sugars. Ketoses, dihydroxyacetone and erythrose. You will see these mainly, so you'll start to see a lot of these sugars as in a lot of other different applications. So in biotech applications, and so these carbohydrates pop their heads up. The ones in the boxes are the ones you will probably want to memorize. For example, here are the 5 carbons: ribulose, xylulose, and fructose. Those are the 5 and 6 carbon ketoses, and they're important. They're the important ones. Okay, so let's talk about hemiacetals and hemiketals. So aldehyde and ketone carbons are very electrophilic. Alcohol oxygen atom is nucleophilic, and then when the aldehydes are attacked by alcohols, hemiacetals form. When ketones are attacked by alcohols, which is what you see in the bottom, you get hemiketals. So the formation of these hemiacetals and hemiketals, they're important because they create a new chiral center at the carbonyl carbon, and what we end up eventually getting, this is a second alcohol as part of another sugar molecule, and that produces the glycosidic bond. So that's kind of the important precursor. Hemiacetals and hemiketals are the important precursor when we talk about forming the glycosidic bond. That's kind of the reduction mechanism that occurs when we do this. That's an important point you're going to want to keep track of. So one of the important things you're going to want to know, and you'll see this very common, you don't commonly see glucose in the linear form. You normally see it as in a circular form, and this because this rarely happens, where the carbonyl carbon becomes the new chiral center, and that's called an anomeric carbon. What happens is the carbonyl oxygen then becomes a hydroxyl group, and this position determines whether a molecule is a alpha or a beta. You can see on the left you have an alpha where the hydroxyl group is on the bottom, okay, and you have on the right you have a beta where the hydroxyl group is on the top, and that's where you get the alpha and the beta circular nature, and you'll see this again and again when we talk about glycosidic bonds. So if it's on the same side, then it's a beta. If it's on the opposite side, it's an alpha. So if it's a cis, beta, trans, alpha. So 5 and 6 member rings are important because there's definite terminology that's associated with them. So we get 6-member oxygen-containing rings are called pyranoses, 5-member rings are called furanoses, and you will notice that we have these rings, things like DNA and other places. Again, you'll see different forms. The anomeric carbon, which is the first carbon in here, which is is usually denoted. It's a new chiral center of the molecule is usually denoted. That oxygen is on the right side with the anomeric carbon. That's usually the formation. So when we're talking about this, we have a very clear understanding of what that means. These are all shown in Hayworth projections, and we even, when we make them disaccharides, we will even follow this rule. So you'll notice that the pyran and furan rings, or pyran and furan rings, are shown in the bottom for your reference, and I would know those structures. So a ring form exists in equilibrium with an open chain form. An aldehyde can, and that's generally true in the free form. As they get to be form-armed structures, that's less true. All of these are reducing. All monosaccharides are reducing, and the free aldehyde group or the free ketone group are the reducing agents. So most disaccharides are, and a few oligosaccharides and polysaccharides are also reducing. Usually there's a reducing end to the oligo and polysaccharides, which we'll talk about again in the next lecture, but you're going to want to know how to identify that. And that's the reducing end is the one with the free ketone or aldehyde group. That's the reducing agent. Again, sugar is classified as a reducing sugar if it has an open chain form with an aldehyde group or a free hemiacetal group. Monosaccharides which contain an aldehyde group are known as aldoses. And those of the ketone group are known as ketoses. Again, that's a review. The aldehyde can be oxidized via a redox reaction in which another compound is reduced. So a reducing sugar is one that reduces certain chemicals. So important identification points and important notes on reducing sugar. So the fact that it's reduced, reduces is also used in glucose in diabetes monitoring, because glucose reducing sugars, there are enzymatic methods that we can quantify the amount of sugar in your blood by converting these. Glucose oxidase will convert these back to, or can be used to create a color, which will then can be measured and tell you exactly how much glucose concentration you have. Also, electrochemical detection can be used in glucose sensors as well by the same oxidation reduction reaction. So this oxidation property is also important in glucose meters for those who have diabetes. We also have hexose derivatives. A lot of these have different additional functional groups. You see these in red or pink in this molecule. We have amino sugars that have amine groups on them. We have deoxy sugars. Obviously, that's important for DNA. We have acidic sugars. We have some of you or your parents may take some of these glucosamines and gluconorate and gluconate and all these others that have different functional groups. This has a carboxyl group. There's certain ones with amino groups. There is a glucose 6-phosphate, which has a phosphate group on it. These are important biochemically relevant carbohydrates that have different functional groups at different positions, and these have served numerous biological and technological biotech applications. All right, so we're going to talk a little bit. I'm going to introduce the glycosidic bond. Two sugar molecules are can be joined together by a glycosidic bond, and between the anomeric carbon and the hydroxyl carbon of a molecule. And the glycosidic bond, which is an acetal between monomers, is less reactive than the hemiacetal, the second monomer, and so the second monomer with the hemiacetal is reducing. An anomeric carbon evolved in the glycosidic linkage is non-reducing. So how does that show up in the real world? So let's just look at this in an example. So we have alpha D glucose. This is the anomeric carbon. We have a hemiacetal. Here's the hydroxyl group on the right, and a beta D glucose. Those two will react in a condensation reaction where H2O is produced to produce a glycosidic bond between. This is the alpha 1, and we have 4. We don't really put in whether it's an alpha or a beta because it's pretty much always an alpha. So it's an alpha 1,4-D, and this is maltose. So if you take alpha D glucopyranosol 1,4 linkage to D glucopyranose, that's exactly what you get, and you get maltose. So you get glucose, an alpha glucose, a beta glucose. There's a hemiacetal reaction, the anomeric carbon on one and the hydroxyl carbon on the other, which happens to be the 5 carbon, linked together to form this alpha 1,4 linkage. Now, two sugar molecules can also be joined at the glycosidic bond between two anomeric carbons. That's when you get a non-reducing disaccharide, and that's when you get non-reducing sugars. If you take the anomeric carbon and put them together, that means there's no reducing ends. And trehalose is an example. It provides a very important protection against drying. You'll also see this in sucrose, So anyway, sucrose is not reducing because it does not have any free ketone or aldehyde, because sucrose does not have any hemiacetal linkages. So again, important concepts to kind of glean from this: anomeric carbon, hydroxyl carbon, acetal groups, hemiacetals, reducing ends. Those are all going to be very important in this whole process, and you'll want to know them for the exam. Here are the very common, again, sucrose, anomeric carbon linkage. It's an alpha 1 2 beta linkage. Lactose, you have a beta 1,4 linkage. Trehalose, you have an alpha 1,1. So this one is sucrose and trehalose are both non-reducing because you have the anomeric carbon linking them together, which means, in essence, means that you can't create long chain hydrocarbons. So you're not going to get polysaccharides out of this, which is the discussion for the next topic. And so we've introduced all the important topics here for this, and as we get going for the next topic, which are polysaccharides, we've introduced the glycosidic bond, and we'll talk about all the different elements that can occur surrounding growing hydrocarbon chains.